Yeah, welcome back. We are now looking at probability theory. So probability measures the likelihood of an outcome, all right? So the probability of an event is a number that is in the interval 0 to 1. That is, if you ever have to calculate the probability of any event or any outcome, the value you get always lies between 0 and 1 or is equal to 0 or 1. When a probability is equal to 0, it means that that event cannot happen. And when a probability is equal to 1, it means that event is sure to happen. Otherwise, it will be any number between 0 and 1, like 0 0.5, 0 0.2, 0 0.09, and so on. So let's say the meteorologist states that the probability that it will rain tomorrow is 20%. So we are saying that the likelihood that tomorrow it will rain is there's a 20% chance that the rains will come tomorrow. So this is the notation we use to represent the probability. This is the probability of something, and that thing is what is put in the bracket here. Let's look at some of the properties of probability. So here are some basic properties of probability. Probabilities are only defined between 0 and 1 inclusive. So the probability of anything is either 0 or 1 or lies between 0 and 1. Number 2, the probability of an empty set is always 0 because an empty set will never happen. That's the probability of nothing. So the probability of such a set is always 0. Number 3, the probability of a sample space is always 1. The sample space consists of all possible elements. So the probability of that space, sample space, definitely it will happen because it consists of all possible elements of that event or that experiment. So that's equal to 1. Now, number 4, if A1, A2, and so on are disjoint events, then the probability of their union is equal to the sum of their probabilities. Okay, so what we are saying here is this. If we have some disjoint events, A1, A2, A3, and so on, the probability of A1 union A2 union A3 and so on is the same as the sum of their probabilities, the probability of A1 plus the probability of A2 plus the probability of A3 plus and so on. So this will have been summarized in our text as such. I running from 1 to infinity is equal to the sum of the probability of I running from 1 to infinity. Right. Let's look at some other very important properties of probability. If A is a subset of B, then the probability of A is less than or equal to the probability of B. So for A to be a subset of B, A has to contain an equal number of or fewer elements than B. So every element in A is also in B. So A can be the same as B or fewer elements than in B. So the probability of A will be less than or equal to B. 2, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. This is the additive law of probability, okay? It assumes that A and B are all belong to one sample space. So why do we subtract the intersection of A and B? Because if A and B have common terms, if you add the probability of A and the probability of B, you would have added those common terms twice. So there's a need to take those ones out once so that it takes care of the double counts of those intersections. Now, if A and B are mutually exclusive, then we say that A intersection, the B is missing from here. A intersection B is equal to 0, okay? Therefore, the probability of A union B will give you simply the probability of A plus the probability of B. So this can be extended to a three member set, okay, where we are looking at A, B, and C. The union of these three sets, okay, the union of these three sets, A, B, and C, is simply adding these three probabilities. Then you subtract the three intersections because they've been counted twice. But if you subtract them 3 times, you need to add back the intersection of A, B, and C. Okay. So once again, we are assuming that A, B, and C are coming from the same sample space. Okay. All right. So we are saying the probability of A union B equals probability of A plus probability of B minus the probability of A intersection B. Using a Venn diagram, A and then B. This is the point of their intersection. All right. So if you are saying the probability of A union B is equal to the probability of A that's the probability of A plus the probability of B. That is this whole thing. Okay. So you realize that this particular session, this space, the intersection, is being counted twice because in working with A, you counted it. In working with B, you counted it. So we've counted it twice, but we needed just one. That's how it's important to go and subtract the intersection once to take care of the double count. In the case of the probability of 3, A union B union C, we are saying it's equal to the probability of A plus probability of B plus the probability of C minus the probability of A intersection B minus probability of A intersection C minus the probability of B intersection C plus the probability of A intersection B intersection C. So using a Venn diagram, this should be A, B, and then C. All right, so let's start. We are saying we want the union of A union B union C, all right? So everything in there, all these three sets combined. So the probability of A is all of this side. Okay, the red aspect here. Now see, you've already counted this space because you consider this whole space. Okay, by considering this whole space, you've also counted a portion of B and C. So in adding probability of B, you have double added this side. You have double added this side. Okay, now in adding C, you have also double added this side and even triple added this side. So that's why it's important to take out, we'll take out A intersection B, which is this side. Let's take it out. Then we take out A intersection C, which is this side. Then we take out B intersection C, which is this side. Because all of those sides were double counted, okay? And it's important that we add back this side because in taking out these three sides, you'd have eliminated this side totally. All right. The fourth one is that the probability of the complement of a set is equal to 1 minus the probability of that set itself. The union of the disjoint events A and A complements must equal the sample space. So once you find the probability of 1A, then the remaining, or the complement of it, is the remaining aspect of the total probability, which should sum up to 1. So if you are saying that the probability of A union A complement is the probability of the sample space, which is equal to 1, then the probability of A union A complement is the probability of A plus the probability of A complements. Take note that A and A complements are disjoint sets. They have no point of intersection. Therefore, we're able to say that the probability of A complement is equal to 1 minus the probability of A. Now, looking at the law of total probability, the law of total probability, let's consider n events, A1, A2, up to AN, which are disjoint, okay? They don't have any point of intersection, such that the sum of all these probabilities is equal to 1 because they all belong to one sample space. Then A1, A2, AN is a partition of some sample space. And a partition is a collection of the sets such that each set is disjoint, all right? Now, suppose B exists in S. There is some set B in X. Then the probability of B is given as this. The probability of B is equal to the probability of B intersection A1 plus B intersection A2 plus all the way to B intersection AN, all right? So this gives us, it's summarized in math notation as such. So this equation we have here, the probability of B equals all of this, is called the law of total probability. So here we see the law of total probability to play where there are just two partitions involved, where we can say that the probability of B, any set B, is equal to the probability of B intersection A plus the probability of B intersection A prime, all right, where all of these belong to one sample space. So we may have a set here, some sets here, and it's partitioned into 4 parts. This is A1, A2, A3, A4. Now we can have some sets B, the set B. So the set B, we are saying that looking at this kind of demonstration, then the probability of B is equal to the probability of B, the aspect of B that intersects with A1. That's this place. Okay, B intersection A1 plus the aspect of B that intersects with A2. Okay, so probability of B intersection A2 plus the aspect of B that intersects with A3. So probability of B intersection. B intersection A3 plus the aspects of B that intersects with A4. Okay. So plus the probability of B intersection A4. So this is what we call the law of total probability. All right, this is the law of total probability. So here I used an illustration where it involved 4 events, A1, A2, A3, and A4. It may involve any number of events. Another property is the De Morgan's law. Now, this law states that the complement of the union of events is equal to the intersection of each of its complements. And the reverse is true. The complement of the intersection of some events is equal to the union of each of its intersection. So in simple terms, using just 2 events, A and B, the De Morgan's law states that the probability of A union B prime is equal to the probability of A prime intersection B prime. And the probability of A intersection B prime is equal to the probability of A prime union B prime. You can use a Venn diagram to show that this is true. Okay. Now, once A union B prime, there should be a bracket around the A union B, is equal to A prime intersection B prime, then the probability of A union B prime should also be equal to the probability of A prime intersection B prime. So the De Morgan's law is saying that the probability of A union B prime is equal to the probability of A prime intersection B prime. And the probability of A intersection B prime is equal to the probability of A prime union B prime. So this is what we call the De Morgan's law. I'm explaining this using just 2 events. You could extend it to a lot more number of events. So I may have a Venn diagram. I want to prove this one, the first one, okay, and show that this is true. I will not do for the second one. So we are saying that if A union B prime is equal to A prime intersection B prime, then the probability of A union B prime is equal to the probability of A prime intersection B prime. Great. Now let's prove this, okay? So we have 2 Venn diagrams. We have A and then B. Then there's another, okay, so let's try and look for this part of the Venn diagram, A union B complement. Now, where's A union B? A union B is everything in A and B combined. So this is the universal set, the sample space. So A union B complement then will be every space outside A union B. So this whole place is A union B complement. So in effect, our A union B complement is the part shaded in red. Now, how about this is for A union B, all complements. How about A complement intersection B complement? So we have A and then B, A, B. First of all, let's shade A complement. So A complement is everything outside A. So everything outside A is A complement within the sample space. all right, within the sample space. And then now let's shade B complement. B complement. Everything outside B is B complement, okay? Everything outside B, but within the sample space is B complement. So I have A complement, I have B complement. What is A intersection, A complement intersection B complement? This is the points where the blue and the green lines intersect, where they meet. And if you look at this diagram very well, if you want to identify that area where the green and the blue line meet, you will realize that this is A, this is B. That area is where green and blue meet is. Sorry, my diagram went away, but that's not a problem. Okay, so this is where we got to. Okay, so we worked on the case where we are trying to now work on A complement intersection B complement. Okay, still on the De Morgan's law. So A and then B. We found A complement to be everything outside A, but within the sample space. And we found B complement to be everything outside B, but within the sample space. So we said that, what's the point of the intersection then? The point of the intersection is the point where the red and the green lines are meeting. Okay, so A and then B. The point where the red and the green lines are meeting, that point is here. This is the area. So if you compare to what we just did with the A union B, all complements, we got the same result, okay? Where the point of their intersection was the area that was shaded red. This is what we got for A union B. So this shows that A union B complement is equal to A complement intersection B complement. Thank you for being a part of this session. I'll see you in the next session.